So this is also important for analysis or for executing it, because this seeing which library functions are called gives you an idea of what the program actually does. And the program also needs this information to execute. So on this, it just contains a list of there's a list of libraries and matching IATs. And the input address table just references function names or function ordinals, which should be imported. And when the TE loader loads the file's memory to execute, it these references to the library names or function names are actually replaced by the actual in-memory addresses of the functions that are referenced. So there's some kind of information loss there. And furthermore, in packed executables, in the packed file, there's typically no imports except for a very minimal set that is needed by the unpacker stub. So the unpacker stub just unpacks the file memory and in the end reconstructs the IAT on the fly. And the IAT is used at runtime just for indirect branches. That means you have in your assembly code, in your machine code, in the process, you have branches that reference the IAT. So that the libraries can change, but it's guaranteed that the actual addresses of the symbols we want to call are referenced by the IAT. So what we do is we go back to our database log of branches, these indirect branches are logged, and see whether there are any indirect branches from the process image into a DLL. Because the locations where these indirect operands are potentially within the input address table. And then we go check these memory regions and see whether they actually reference exported symbols or libraries and try to reconstruct a useful performance for the TE loader. So this is a very simple method, but it works in this case. A certain amount of time after I had finished the unpacker project, I touched up the code a little, made sure it would actually compile on more than one of my development systems, and started hacking on it again from time to time. And what I implemented then was API call tracing. Because I thought, well, branch instructions are implemented anyway. I take note of every branch instruction, so it shouldn't be that much more expensive computationally to just check whether the branch target is an API function. So using this information, I can at least see which functions are being called. But then it would be nice to know whether there's what the operands are on the stack. What values are these functions being called with? So for that, we need to know the actual function prototype and computationally derive the stack layout to, grab the argument from the stack and reconstruct it. And this is where I came across a nice little project called XML. I think unfortunately it's not being highly maintained at the moment, but it's basically a patch to a GCC, which can take any C++ program or even just header files as input and generate XML output. The XML looks like this. It's hard to see here. So you can see you have an XML element for a function. The function name is get from address. It has a return type of this ID. It's located in file 2, line 2610. Again, we have attributes, calling convention, And we have some arguments there. One is named HModule of type 8702, and we have another argument called HPPROM. And we get also all kinds of other information about the argument type, say 6677, say type there. The name is long pointer string. The actual type is this. This is a pointer type, which points to this type and so forth. So we can deduct the actual type, function prototype of the function and the argument and the types and type. See here, the type is also this is 8 bits. And luckily, there's also a Python extension that can take these XML files as input, and here's a nice API to pre-read functions by name, inspect function prototypes, and thus construct a stack layout for function calls. And current implementation is not very advanced. Can handle character strings, integers, and for lack of a better implementation, just takes a look at them once for the function call, and then outputs them one, and the return value when the function returns. What are the results of this solution? During my thesis, I should generate some numbers to say something about the performance of my project. And some of the criteria there: unpacking time, the correctness of OEP detection. Is the unpacked code actually that what the runtime packet actually packed before? And in the end, could I reconstruct a valid and executable the image? And I evaluated this in two ways. One was a set of synthetic samples. The other